Whoops, started the wrong timer. So I think it's an interesting time in computer architecture and in cloud computing. Because as you saw in David's talk, if you attended that talk, there's incredible distributed systems being built, and they're increasingly becoming commodity and available to you as an end user, often for quite cheaply. So what I want to talk about is a specific kind of journey that I think is leading us towards a new kind of computer, perhaps even a supercomputer accessible in the cloud. And this journey starts about 5 years ago when Amazon, one of the largest, in fact, the largest cloud provider, announced a new service that they aptly called Lambda. And they called it Lambda because it was the idea that you can take a function. Here one is shown in Node.js, does simple hello world, and you can instantly make it reactive. So you can take this function, deploy it to the cloud, and as it receives events, the cloud provider's responsibility is to instantly, or near instantly, provision resources to run this function, gather the result, and send it back to wherever it needs to. And if you have more events, more Lambdas run. And the idea is that you do this without having to actually do a whole lot of work at all. And if the network cooperates, so that you believe me, I'll show you a quick demo. And it's really as simple as defining a function, and then it's accessible, for example, in your web browser. So let's see. So font hopefully is big enough you can see. So I just defined a function, same one I had in the slide, and it's accessible over the web. There it is. That's it. It's that simple. And now you can imagine that you can do more interesting functions, of course. So imagine, for example, you have a big cat picture, and it's too big, and you'd like to make it small. So here's some code on GitHub, which takes an image and then resizes it. And without even actually deploying this code, you probably can't make out this URL, but this is essentially running on a serverless cloud. It's pointing to the GitHub function, and it receives a URL to the cat. And when this function runs, now I have a miniaturized or thumbnail picture of the cat. And I did this without having to do a whole lot of work, in the sense of this is acting like a server, but I wrote no server code at all. I didn't say wait for a request on a particular route, and when that happens, invoke a function. In fact, I provisioned no servers at all. Right? This runs instantly, and it's available in the cloud. And I didn't dare to run a load test from here, but you could generate hundreds or thousands of requests against this system, against this function. In fact, you can hit the bit.ly URL, and you'll be actually running this function in the cloud, all with no work. Right? So this model of computing, I think, is very powerful. It's not that I can just do this with Node.js. I can, in fact, do this with a lot of different languages. Almost any language, because one of the models here is just about anything you can package up into a canonical representation, including containers, you can run in this model. So drive this point home. This is a PHP function. I'm just going to run it. I could do this for Go. So what's interesting about Go, unlike PHP and JavaScript, is it's a compiled language. I'm just going to run it. It just runs. I didn't even compile it. Right? I can publish this URL and click on this URL, and there it is. And in fact, you can send it query parameters. It just runs. Right? So the beauty and simplicity of this model is how accessible it really makes distributed system in the cloud with a very friendly developer experience. And so about 2 years after Amazon announced Lambda, this word serverless started to enter lexicon. Because as I showed you, I wrote no server code, I provisioned no servers, and yet my code is essentially serving up requests and handling lots of load, all for free. And serverless has many benefits. I illustrated quite quickly, right, this ability that you can run functions, make them reactive, they can scale automatically. But some other aspects, like this code is running on a machine that's automatically secured for me. The OS is automatically patched. The kernel is automatically patched. I have to worry about nothing related to the operation of this machine. And moreover, it changes the economics of how I pay for these services. So rather than renting a server or buying a server and then paying the utility bill for it, I just pay for when my function runs and services requests. So it's a utility model down to the level of milliseconds. And this means that you can have 1,000-way parallelism. You can have literally thousands of functions running. And not only that, you can do millions of operations, and it would cost you near nothing. Right? So it's about a quarter for certain kinds of functions that you can run. Of course, the costs change depending on what you're actually doing and how long your functions run. And that kind of capability or compute power is being noticed. And it's being noticed in academia. This is just a highlight of some of the papers that have been published recently that are looking at how do you actually do high-performance computing on top of this substrate. So a couple of papers from Berkeley on the system they're working on called Pyren, which is really just HPC on top of serverless functions. There's some work from Stanford for Gigi, looking at essentially how do you rethink compilation for large systems like the Linux kernel when you can essentially distribute the jobs and do them all in the cloud. Video encoding. Right? So can you actually do this for video processing? And in fact, you can. But it's not all academic. Entire companies are in fact undergoing through digital transformations that are being led from the ground up. So small teams of developers are completely disrupting within their organizations how they develop for the cloud. Coca-Cola, iRobot, Capital One, these are large companies in the US, and some of them are global, of course. Small teams are able to execute much faster than traditional sort of server and microservices style development. They're able to do it often with cost savings. And what it really boils down to is they can focus on value and value creation for their organization and their customers. They don't have to worry about the details of how many servers do I need. They don't have to worry about how do I secure the servers and patch them and manage them. I have to worry about where are my logs going, how do I aggregate them. All of that comes for free as part of the serverless platform. And the investor community is also noticing. So in 2018 alone, $100 million was sort of committed to entrepreneurs that are looking at problems and technical gaps in the serverless space. Nimbella, the company that I co-founded, is one of them. So we're part of the statistic. So there's a lot of excitement in this field. Because if you think about it in terms of what it enables, I think it's really rich. I'm going to try to convey some more points of that. So in my view, the cloud landscape is really changing. In fact, I would even argue this has already changed. And this is a natural evolution of our history of computing. Right? Over decades, we have increasingly worked towards greater automation, greater abstraction. And that's just the history of our computing, all the way back to Fortran and the mainframe, with the introduction of the first instruction set architecture. So you shift from on-premise infrastructure to the era of infrastructure and platforms as service, where you can rent machines by the hour, to functions as a service, where you just pay per request. And to give you a sense of scale, in 2015, just a few months after Amazon announced Lambda, they were processing about 2 billion invocations a month. So these are essentially how many times did customers run functions on their platform. In 2019, it's over 2 trillion. That's an exponential kind of growth. But as much as this number is really big, it's actually a tiny fraction of all the compute in the cloud. So I think we're still early in sort of this journey towards serverless and massive adoption of serverless. But I believe it's inevitable. It will happen. And it's a matter of actually building more abstractions and giving better tools to end users to essentially adopt this technology. And so with some levity, I think that the number of servers that organizations, academic institutions manage over time will decrease. And so I say that they will decrease in half every 18 months. There are limits, of course. Otherwise, this would be too good to be true. And I want to frame those limits in terms of a serverless contract. In short, this is like, what is the variance on my execution time? Stated in other words, right, I don't only care that the service is always up to run my functions, but I want to know how long does it take to run functions. So if I have requests, and depending on the workload, is it the case that these these functions take a long time to run, or do they run instantly? How much system overhead, in other words, is there when I adopt a system? Because that can dictate the kinds of workloads that you use, or that kind of workloads that you can adopt this technology for. And so without getting into Little's law and queuing theory, I think you can grasp the intuition by just looking at two terms: the arrival rate, A, and the drain rate, D. So arrival rate says how often do requests come, so how often is the system accepting function invocations. And then drain rate is essentially how fast are the functions essentially releasing their resources and exiting the system. And in the happy case, from an end user's perspective, when the system is over-provisioned, so that means that the arrival rate is much less than the drain rate, the queuing latency is near zero. So that's not ideal from the system provider's point of view, because it means they have excess capacity in the system they're not monetizing. The ideal case, of course, is when the arrival rate and the drain rate are about the same. That means queuing latency is still near zero, so you have very little overhead introduced by the system. But this is very difficult to achieve, because the offered load on the system is variable. It's difficult to predict. And moreover, you don't know how long these functions are going to hold on to their resources. The unhappy case, from an end user's perspective, is when the system is under-provisioned. And so requests are coming in, you don't have enough resources to run them. And so the queuing latency now becomes proportional to mismatch between the arrival rate and the drain rate. And to give you the ability to essentially tap into serverless elasticity, basically that the cloud provider has thousands of machines in their data center, right? They have to be able to provision resources to run your functions. And the kinds of resources that they use dictates what kind of policies they can have on sort of the whole serverless experience. And it's not just about provisioning resources, it's also about isolating your function so that two users who might be sharing the same machine cannot observe each other's executions, cannot attack each other, and what other security mechanisms you need in place. So there's different ways of isolating function executions, from VMs, which are potentially the most secure, to V8 isolates, which is a way of sandboxing execution of JavaScript and WebAssembly. Think of it as process-level isolation. Containers are in the middle, and the far majority of functions that run in the cloud today are isolated inside containers. There's two orders of magnitude difference in the performance of each of these models. And this has spurred a lot of interest in other ways of sort of providing the security benefits of a VM, but with the performance characteristics of isolates. So unikernels and micro VMs. Micro VMs in particular, I'm calling it out because Amazon announced Firecracker about a year ago. And Firecracker is their new technology for isolation. It's a micro VM. It basically sheds all of the things, the entire set of components you don't need in a VM when you're running functions, throws them out. And by doing that, you can actually reduce the startup time of VMs to be actually better than containers under load. And so there's a lot of interesting work that's happening in this space to sort of give you better performance and better isolation, better security guarantees. And you can see this as an end user. So for a load test that I ran, I sort of captured 1,000 of those activations yesterday. And for the most part, blue is good in terms of uniformity, but you'll see there's a couple of pixels that are sort of off color. These are slower according to the scale. And if I dig down deeper into the pathologies of what's happening in the system, these latencies here are sort of time spent waiting in the system to execute the function. This is time actually executing your function. And this long delay here is time actually allocating a new resource. So the system is employing different heuristics for scheduling your functions. And depending on the choices it makes, you might wait more, you might wait less, and in some cases, you have to provision new resources for them. And you can understand this by sort of thinking about what's happening in the scheduler. It's essentially doing bin packing. And it's the illustration here is you have many servers running many Lambdas from different users. And you have a new request. Where do you stick it? Do you allocate it on a new server? Do you wait for a resource to be finished, like in this case, and then try to reuse the resources that you've allocated for it. And so the choice that the scheduler makes impacts the overall execution time of your function and how much system overhead there is in the system. So this area of scheduling is actually very interesting to me. And I'd like to make an analogy to the reduced instruction set architecture, because I think there's lots of ideas from microarchitecture that you can apply in this space if you just shift the perspective from which you're looking at what's happening in the system. And in a simplified RISC pipeline, right, you have instruction fetch, instruction decode, execute, and write back. And instruction fetch in the serverless model for functions is you have to fetch the function. So there's still code that I have to run. I have to fetch it from somewhere, and I have to essentially prepare it for execution. I will cache this function so that if there's repeated function executions, I don't have to go back to the expensive data store every time. Instruction decode essentially goes down to the point of saying, well, this is a JavaScript function. I need a JavaScript resource to run it. It's a JVM. I may need to compile it before I can run it. It's a Java function, so I need a JVM to run it. And you might even need specialized resources like a GPU. The execute phase is when you actually run the function and grab the result, and then write back is when you send the result back to a data store. And so with the RISC architecture, we do a lot of different optimizations to improve the pipelining and the efficiency of the system. Branch prediction, speculation, register bypass. And there's very similar things that you could do in the functions model for serverless. So branch prediction can become function prediction. Can you predict which load you're about to hit? And if so, use that as a way of improving the scheduling technology. Speculation goes towards pre-warming. So if you know you're about to receive different kinds of functions to execute and you need different resources for them, can you pre-allocate them? And then register bypass essentially goes towards function-to-function communication. So the result of one function becomes the input to another function. And a lot of these techniques are not actually being used today, as far as I know. We're certainly not using them in the systems that we've built. And so the serverless contract, getting back to that in terms of, what is the execution time, the system overhead you can expect in terms of the functions that you're running, comes down to a constraint, a very hard constraint that the system puts on your functions. They must run in finite time and in finite space. Furthermore, they must have transient residency. Another way of saying this is that your functions are stateless because you don't know which machines they're going to run on, so you can't even store state and persist it to the file system, and they're going to move around in the system. They might run completely different geographies even. And because time is finite, you cannot violate this. Death is certain. The function will be killed by the service provider if it actually tries to exceed its time limit or tries to use more memory than is pre-allocated for it. The saving grace, though, is that revival is fast, right? As I've tried to illustrate, is that your functions can run very fast in the system, even under the constraints that it might be servicing lots of load. So it means that you can, in fact, do very long-running functions. It's just not in the style that you might be accustomed to. So it really goes down towards the notion of function composition. Can you take applications and build them in a serverless way where you can use programming language constructs like modularity? So I can take a function, compose them together. Can I treat that composition as a further function, as a module that then I can further compose? So in Onward 17, we explored this idea, and we showed there's different ways of orchestrating a function composition and essentially come up with a serverless application that spans many different functions. I'll quickly go through them to illustrate different points and their trade-offs. So client-side composition says, I have lots of functions, I know what I want to invoke, and I'm going to orchestrate the execution and data flow between them, but from an external client. It could be my browser, for example. That composition model works, but it doesn't fit in terms of substitution. This is not a further composable composition. That's because I can't take your browser or the code that's running on your desktop and then use it in another application. So we call this property substitution. Functions that are composed together should still look like functions. Reflective composition is where you move this orchestrator and just run it as a function itself. So now imagine that I have a function which is effectively calling other functions from within the system. That works with two constraints. One is that there's still a time limit on this new function which is doing the scheduling. And the second, the call stack, if you will, of the calling function, the main, is still live while the subsequent functions are also running. So we call this property double billing. You can sort of illustrate that by the timeline on top. Right? The call stack for the top function is live and sort of covers all of the subsequent functions. So we'd like to get rid of double billing. Well, you can also say, well, I have all the source code potentially. Why not just fuse all the functions? That works and is actually very efficient, but then restricts you in terms of the kinds of compositions you can do. Right? One of the points I made earlier is that you can essentially use this model where you can deploy functions in many different languages. So it allows you to use the right language for the right job. The majority of functions today are in Python because of a lot of interest in machine learning, and in JavaScript because a lot of interest in sort of web-based APIs. Java is another popular one. Go is increasingly there. So this model of fusion works as long as your entire application is a single language. But there are constraints, right? Because now you're doing function fusion, which is equivalent to function inlining in a classic sense. But you have to make sure that your inline code still fits within the time frame or the time bound that the overall system imposes, and the resources that it consumes do not exceed the system resource limits that are in there. So we call this property black box, and that you want to treat the functions as black boxes. You can't look inside them, you can't modify them. And so if you want a composition that actually satisfies all three, it's very difficult to achieve at user level. Continuations get you quite close. So with continuations, when a function completes, it can essentially fire a trigger that says, I'm done, here's my result. And then next execution can essentially be fired by a rule that picks up that result and keeps going. So it's in the right direction, it works. But at user level, that means I, as an end user consuming a platform that wants to do this, I can't without breaking one of the other properties, substitution, double billing, or black box. So we formulated this as the serverless trilemma. And there are different ways of sort of realizing serverless compositions, but unless the platform itself essentially provides a mechanism for function-to-function communication, it's difficult to achieve. In fact, we don't believe it's possible to achieve without breaking one of these constraints. Now, there are constraints in the design space, and it's plausible that you can choose different points in the design space. In fact, Amazon has a service for workflow orchestration that they've repurposed for as step functions, and so it allows you to do function composition. They don't respect the substitution property, and that's a choice that they make, and it's completely valid. They also charge a significant amount of money over just running functions composition. So it's an interesting economic argument for maybe breaking some of these properties. So some of the work that we've done, going back to my time at IBM, was looking at programming models for serverless composition. And we had been working on a system that we've open sourced as Apache OpenWhisk. It is essentially a competitor, I don't want to call it a competitor, it's an open source implementation of a serverless functions platform. And it's run by IBM Cloud Functions, essentially as the same code base as running its IBM Cloud as a service. Adobe IO Runtime also uses this technology. Naver and Nimbella, we use it at my company. And it was built for the enterprise because shortly after Amazon was announced, we sort of realized there's a great opportunity here. And so we built a system that eventually launched as IBM Cloud Functions, but we launched it out of research, out of IBM research. So we were asking also research questions at the time, including the composition issue. So it's built for research. And in fact, I'm going to get back to that shortly. And to give you a sense of the kind of compositions you could do on top of this model, we didn't invent a new language, but we built essentially a language that allows you to describe combinators, control flow combinators, that you can describe in JavaScript. There's now a Python library as well that has a visual representation and an underlying machine model. We don't do a lot of compiler transformations on this language today. And this was essentially our first attempt at coming up with a serverless composition programming model. It allows you to see, as you can see from the visual representation, have sort of traditional control flow. You can do an if then else at the level of compositions of functions. You can even do while loops. So this is a document splitter. It takes a large document, splits it into individual pages, and then does different transformations on each page, depending on the file type or anything else that might be there. So you can write while loops. You can write if then else. So it's interesting in that perspective. And yesterday, Abhinav Jangda from UMass Amherst gave a talk that sort of formalized this notion of serverless computing in what they call lambda. And it helps users or developers think about the semantics of their execution, particularly in the face of errors. So what happens when your function dies? Is it retried by the system? What if you actually did try to externalize state and your function died halfway in the middle? How do you think about that? So it's an interesting paper, highly recommend reading it, if this is a topic that excites you. And as part of their implementation, and also in this paper which was presented last week at Micro, looking at architecture implications from functions as a service, serverless functions, both of these papers actually made use of OpenWhisk. So just to emphasize the point that there are lots of interesting research questions still to be asked and answered in the context of serverless. And Apache OpenWhisk is a good vehicle to do that kind of experimentation and evaluation, because not only is it production ready, and it's actually running at enterprise scale, you can actually do interesting research within this framework and address some of the challenges in the technology gap. So serverless and functions today is really just about the CPU. It's about the compute. But a computer is not just a CPU, right? You have memory, and in fact, the memory aspect is completely missing from today's serverless technology, right? The platforms lift their hands and say, your function should be stateless. And if you try to do anything stateful, well, then you're inheriting and you're buying into the entire burden of managing that state, meaning dealing with things like failures and resiliency in the face of those failures. And so why I think we're at the dawn of a new cloud computer is because while there's serverless compute, increasingly, I think the future is in serverless memory and the combination of the two. And once you have the two, now you have a cloud computer. Now you can actually do more interesting applications. Because that composition I showed you before should look like a data flow graph. Right? If you just treat every node as it's a function, yes, but it's just a node in the graph. I can look at the history of data flow transformations and now how they're mapped to distributed systems and now apply them in this context. And so there's a big gap today between the microarchitecture and applications. And in computing, when we look at sort of how do you bridge that gap, well, we introduced an ISA, right? And the introduction of the ISA for the mainframe allowed the evolution of Fortran, and then the rest is history, as they say. And we're faced today where we don't quite have an ISA for the instruction set. We don't have an instruction set architecture for the cloud computer. And that's kind of important to sort of enable the next phases of evolution and technology innovation in the stack, helping you bridge from the underlying substrate all the way up to the application levels. So we have applications because there are enterprises and academics who are building interesting use cases on top of the cloud providers, which you can treat as a commodity for the most part. And we have, somewhere in the space, some capabilities to do serverless compositions, but there's still large gaps from the applications that people are writing and then the cloud providers, which are providing the substrate for execution. And so part of our work, most recently, and the things that we're working on at my company, is helping to define the instruction set architecture for the cloud computer. We treat the cloud providers as complete commodity. They exist, they're massively scalable, and as you saw in David's talk, companies like Google and Amazon and Microsoft are incredibly good at sort of building large-scale distributed systems that work. So we just build on top of that. But what we need to focus on is the function-to-function communication between functions within the platform, making that fast, making that reliable, and having low latency, access to low latency storage. So the ability to provide caching and the ability to store and persist state that's accessible to functions with very low latencies. This is hard, right? It's hard because functions, as I've shown you, have transient residency and sort of satisfy the serverless contract that allows the providers to give you or deliver on the serverless promise of elasticity and near infinite capacity. They have to impose hard bounds, and some of those hard bounds are things like finite execution time and finite resources. And the transient residency kills locality, right? So as an end user, if you're running functions, you don't know which machines they're running on. And so if you're doing something like machine learning or machine inference, where you're loading a machine model every time to run your function from an external store to your function, and you have thousands of instances of those functions, there's no notion of locality. You're going to end up fetching that data store from that data store every time you run a function, and that's expensive. And so what you need is a notion of data locality, and you need to introduce that back into the computing model. And it can only be done, just like with serverless compositions and serverless trilemma, it can only be done at the platform level. And so at Nimbella, this is part of the work that we're working on. It's serverless plus stateful. So we're trying to extend the set of workloads that you can use serverless technology for. And it's not that you can't do this today, right? So I can take a Lambda function. In fact, there's one in the UMass Amherst paper yesterday, I think, does a nice illustration of the complexity involved in going from a stateless function to a stateful function when you want to introduce state into your computation. But I can certainly do this. I can break my function down to reading from a memory store. I can provision, say, a Redis instance or some other data store. I can read from it, perform my computation right back to it, and deal with all the potential failure modes that can happen. It's absolutely doable, and you can do that at user level. But it's error prone. It's complicated. It's potentially complicated. And so part of our abstraction is to sort of treat this from a classic sense of these are actors. The function is an actor. It can receive state as part of its execution in addition to the event. And if we can break up the computation, sort of treat every execution as having canonical precondition, execution, and post-condition, then we can make the read state and the write state components system managed. And by introducing that kind of abstraction, it sort of allows us to move data around to where the compute is, or move the compute to where the data is. By taking it away from the end user's perspective, essentially it introduces the same kind of serverless abstractions for compute, but now at the data level. We're not quite there. Part of what we've done today is introduce a completely managed data store for functions, but it's at this point today, it's exposed to the end user. But part of our vision is essentially make it completely hidden and bring this notion of serverless compute plus serverless memory to the end users. And so I wanted to conclude, I'll try to do one more demo at the end because I think I have time, with a quote from Tim Wagner, who's the Amazon Lambda inventor. And so he recently gave a talk about his view of serverless and where it's going. And in fact, he had a view that's very similar, except he called it serverless supercomputer. And in his notion, he essentially points out that distributed computing research has modeled capacity. When you're building applications, you model capacity as fixed, right? You're mapping a distributed application to fixed resources, but time is unlimited, right? Your functions can run for a long period of time. But with serverless, right, because of this hard notion on execution time, which has been relaxed over time. So when Lambda was announced, your time limit was 5 minutes. And now you can run for up to 15 minutes, for example. But with serverless, because time is limited, and that's a hard balance, that's a new constraint. Capacity, on the other hand, is completely infinite. And some of the academic work that I showed earlier is taking advantage of that and bringing capabilities of high-performance computing on top of this model. And this only changes everything, as he put it. And I believe that. And so I think there's lots of interesting research areas and many PhD theses to be written on top of this model of computing, from the notion of different schedulers, different scheduling technology, different isolation technology, formal models, queuing theory, programming languages, compilers, basically everything within that abstraction gap stack that I showed earlier. I have time, right, to do one quick demo? So I wrote this demo yesterday and then realized the network bandwidth wasn't going to let me do exactly everything I wanted to do. So this is a function this is a couple of functions that sort of illustrate integrated storage. And what this function does is, maybe I should show it first. Let's kill this. It's going to do image recognition, and I'm uploading an image. Hopefully that'll work. And submit it. Okay. Right. So I just wrote some text, took a screenshot of it. That's what I just uploaded. And the function itself is fairly small. I'm using a node package called Tesseract to do the image recognition. This is essentially, it's going to download the machine model that's been pre-trained, and then it just runs. And the execution essentially says, you're going to get a file name. And so the upload actually just sent the code to an object store. It's an object store that wasn't provisioned by the end user. Just like with functions, you create a function, you just deploy it. It's the same model here. The application just says, here's a file, right? And then it just gets back a handle. And that handle essentially ends up in this function under file name. And then it's going to do some recognition. And if everything is successful, it will return the results. It's a few lines of code. And then the second part of it is text-to-speech. So here I'm just making an API call to Google, Google Translate, which is going to take the results of the image recognition and essentially return a URL with the text that I can use in the service. So hopefully you can see it, but basically it recognizes the text there, and I can speak it.
I do not like green eggs and ham.
Right.
I do not like them, Sam, I am.
Okay, so I have young kids. They love this book. I've read it a million times. And so I'm just going to look at the activations that actually ran. Sorry, a little small there. Right, so you see there's several executions. There's the hellos there. Interesting, maybe some of you have been running the hello function. Right, there's some credentialing. I had to get some secrets to actually make API calls to Google service. Image to text took 14 seconds. And you see these were essentially cold starts. There's a little bit of initialization time here and here. And the text-to-speech was really fast because all it's doing is just transliterating the input to an API call. And I can click this and actually see that, here's the result of the activation. And you look at the logs. As the execution was happening, it was emitting logs saying essentially how much progress it has made. Right? All of this for free. Basically, all I wrote was my functions, which is the value that I wanted to deliver. And everything else the serverless platform delivers for you. Right? I think this is the capability and sort of the compute power of this computing model and why it makes me excited, essentially about making supercomputers accessible to end users for essentially nothing with a programming experience that I think should look increasingly familiar to development, traditional and classic development. That's it. Thank you.
All right, questions? Sasha?
Okay, so I really like the analogy of kind of the serverless architecture to the traditional computing architecture. I have two questions. One is a time restriction somehow inherent?
Yes.
And the second question is more about, I guess, the programming model is like, how it seems like it might become a issue of how do you split up these functions, right? Like you could really go crazy and split up everything into a function, like people go crazy with microservices. But at some point, then you get diminishing returns and maybe even it's counterproductive.
Right, and so the time constraint, I think, is, so there are two questions. One is a time constraint inherent? I believe the answer is yes, and that was part of the serverless contract, right? For me as a service provider, or as any of the cloud providers, to give you this elasticity, it has to know how much is your function going to run for, because the longer your function runs, the more resources I need to provide to service new requests. And so to mitigate sort of against the risk of having infinite capacity, and it's part of the policy that I have to define on when do I stop accepting requests and start rejecting them, you have to put a cap on essentially the whole time for resources. Now, as the data centers get bigger, or as new data centers pop up, there's more and more compute available, and you're able to harness sort of all the idle cycles in your data center. Those constraints are increasingly relaxed. So within 5 years, we've gone from 5 minutes to 15 minutes, I think, either on Amazon or Google. And those limits, I think, will continue to increase. But it's not going to be the case, in my view, that you can just run for an infinite amount of time in this model. There's other things you can do as opposed to where if your function starts to look more like a traditional microservice, something that's just going to be long running or run for days, you can do function promotion, right? And in my view, that should just be naturally done by the platform. If something is receiving enough load and you want to persist it and give it better connection and sort of bypass a lot of the system for efficiency, the system should just do that magically and automatically, not expose it to the end user. The other point about, at what point do you stop breaking down your computation, that's part of why we were asking the serverless composition questions. And sort of the analogy and the way I think about it is when you're parallel programming or you're programming against a parallel abstraction, if you start from fine-grained components, it's easier for the compiler to fuse them together and coarsen the execution, as opposed to doing automatic parallelization that takes a large monolithic piece of code and break it down. So if you can give the right abstractions to where users write functions and are modular, then it's easier to potentially do serverless composition and the transformations to fuse things back, as opposed to the other way around. But these are part of the gap between the applications people are increasingly want to build on this platform and where we are today. Right. Yeah. So the question is about the development experience and how do you actually develop and debug in this world where it's largely printf. And I still think, the reason I call this the dawn of the cloud computer is because it's like the Fortran days of where we are with serverless. And a lot of that VC money, that $100 million that was invested last year, is going towards companies that are trying to address that issue with respect to better tooling and better observability. Part of some of what we've done with Apache OpenWhisk is allowing you to run the entire stack locally and matches exactly what you're running in the cloud. But by running it locally in a very lightweight mode, you can actually attach debuggers to your function so that you can actually intercept the execution, set breakpoints, set watch points. In terms of the code running in production and being able to observe that, the model that's increasingly popular is essentially, because we control the runtime environment that your functions run in, is adding instrumentation within the functions, sort of as a base layer. It's just there. And that generates lots of data, even lets you essentially connect a WebSocket over some other port, so you can do debugging in vivo. But I think that's an open problem. There's lots of interesting challenges in terms of debugging and better observability at this scale. Any other questions?
So, one question. So, how do you address fault tolerance without going whole hog with things like Kafka or Hyperledger?
Right. Read their paper. I think, right, this is an interesting challenge also in the model today. And there's different providers have chosen different models for handling errors. But the burden falls entirely on the end user today. You have to code against failure. And in one model, the execution may or may not happen. And another model, the execution may happen more than once. There is no exactly one semantics yet. And so if you're trying to do something that's transactional, that burden falls largely on you. And I think that's another gap and another interesting research direction that needs to be filled. And my view is that these kinds of problems aren't going to be solved necessarily by the cloud providers because they're busy building the cloud infrastructure. And these are the kinds of innovations that happen in academia and entrepreneurship. Thank you.